has returned, so we'll have him go third, and that is Christoph Jacobi, and he will speak to us about ionospheric response to solar UV radiation variations. Christoph, are you on?
Yeah, thank you very much. I'm sorry for that. We had just some problems with this with internet connection, and so I had to change the office. I hope it works. Do you see my screen?
Yes, and thank you for staying up late to talk to us.
Yeah, thank you very much. So wrong way. So I would like to talk a bit about the ionospheric response to solar UV changes at timescales of a few days or so. And so there is some delay in that. And what we wanted to do is to analyze it. This might be interesting to have that because solar UV variations are responsible for the changes and the variability of the ionosphere. And if there is this delay, and if you know that, it could be helpful, for example, for empirical models or other things that you can use for the ionosphere. So this work has mostly been done by two PhD students, it was Rajesh and Eric, and more or less everything that is a little bit more new is from Rajesh and Eric's papers that I had here. So I would go only briefly for ionospheric variability and just present some results of this delay, what we have observed, and some attempt to model it to get some more idea about what is the delay, how it is distributed in time and in space, and a little bit on processes for here. So these figures are only a little bit about the ionosphere. Maybe for this TEC map, what you see here, we have, if we want to know a global, something on a global scale, these observations by GPS ground-based receivers are very suitable. They're globally distributed. And of course, the gaps in there are filled by some model. But if you stay somewhere, let's say in America, US and America or Japan or so, in some regions where there are more dense receivers, it's very close to an observation and can be used, let's say, for validating of models or for some studies what one can do. Well, so just very briefly, so this is what we have for TEC. So this is latitude, and here some 19 years or so. And it's of course varying with the solar cycle. And there is more. There is an annual cycle that you see more very nicely here in solar minimum. There is a semi-annual cycle, which is let's say not connected with the solar variability, but dynamically, and there's some more short-term variability which you cannot see at that scale. So down here, it's a figure by Rajesh. He tried to look at that in connection with a lot of different solar proxies, and well, in principle, you can see that some of the variability is solar connected, and some at this time scales is not. But this is not that what I wanted to talk about, but on a time scale of the solar rotation, and about that, what is connected with EUV and some differences. So electron density also is dependent on ionization and recombination, and then the last one is transport. And this ionization is very quick and quasi instantaneous. And if you calculate this through the UV flux, it is very close here. But TEC, of course, is not. And the scatter, what you see here, that could be through this recombination, what is not so fast and is so to a certain degree delayed. And also there is transport, of course, so that you get a correlation of only 0.9 or so. This is daily data. At even shorter timescales, it's even different. So, and so what we have here is only part of a time series. That's only 3 years, and the red curve. This is the daily EUV flux. It's just integrated here, and the green, light green curve. That's the global mean total electron content. So. As some sort of a first proxy of global ionization. So, and what you can see is first, it's this trend here. This is in the course of the solar cycle. Then you have the semi-annual oscillation. This where we have it here. And you see that it is connected here. In this year, it's more or less by chance together with the UV flux, but in these 2 years here, it is not dependent on, it's not due to the UV, to the solar radiation. And what we would like to focus on is here is a 27-day solar rotation. This is particularly strong here in 2012. And so I would focus a little bit more on that. But the first what we did was to filter this time series in a very narrow band. It's only from 25 to 29 days, so it's really only 27 days. And here you see that it's really very well connected with the UV variability and very close together with a little bit of a difference, maybe, but this is relatively small, at least in this connection. So the 27-day was relatively strong in 2012. So zoom again into this one and into this one. And here you can see it, again, this filtered data set. And here you can see this delay. So you see this, this means the flux, and it comes about 1 day earlier. This is all the time here. At some points you can see it in more detail. In others, maybe not so nicely. Okay, this was 1 day, and this is relatively regular. If you look into cross correlation, it's maybe a little bit difficult to see. So this is the lag here, and this is a time scale. So at different time scales. So here, this was the 27-day oscillation, where the lag is about 1 day, and maybe if you go to longer time scales, there is a tendency that this lag is longer somehow. We didn't go further in this analysis of the long time scales because it was more or less one particular time interval that it showed up. And during the rest of the time, this 27-day oscillation is there more or less every year, all the time. So we focused on that again. So we had this delay, it's about 1 day. Well, so one attempt was to model that. The first was just simply to see whether it is reproduced in a model or not. So we used the CTIP-E model. It is relatively simple, easy to use. It has lower boundary, 80 kilometers. There you need some sort of atmosphere below. And then you have the neutral and the ionized atmosphere, some electrodynamics and magnetosphere. The solar radiation is parameterized using a reference spectrum, and this is modulated if you want to have more or less solar flux by using the F10.7 index. So this is for these figures with the modeling. The solar variability is always shown in terms of an F10.7 variability. Okay, so this is Raj's work, and he tried that so to fit some sort of a 27-day cycle, and this is what we get as total electron content. So look reasonable, well, in terms of the climatology, but also in terms of this 27-day cycle, what he obtained. If you look here, is that the maximum here is some day 14 or so, and the maximum here is a little bit later. And if you take the global TEC, which he calls GTEC, global scale There you also see in the model this delay here. We have a cross correlation at a lag of 1 day. You see that seems to be maximum. So the model was really in the first attempt. You don't have to do very much. It was able to see the delay, and this is only one thing. He tried to look into some different processes or some sort of a climatology. He used an example with higher solar activity with a 10.7 over 150 or so, and very low solar activity, and found that in this case the delay is 1 day, but in the very high solar activity it goes to 2 days. By the way, if you look into observations, it's a little bit different, but this is because we do not have a real atmosphere below, and atmospheric disturbances usually with low solar activity, then meteorological influence become more dominant in the ionosphere, and you have a slightly different result. This is for, let's say, meteorological undisturbed condition. Then at high solar activity you have some longer delay. So this was something from modeling, and now this is Eric's work. He was looking into more details, which means not using daily data or so, but using high resolution. In our case, this means 1 hour data. And so this was also from SDO. Looking here for an example, it's in 2012, checking the cross correlation, and this is of course here the 27 days. Of course now the correlation is weaker, much weaker than if you use daily data. And but what you can see here in this peak, this is just zooming in into here, that the delay is not 1 day, it is about 17 hours. So one can look into this with more detail, or he was able to look into this with more detail, and then did this also for some 3 years where he got the data here, higher resolution TEC and higher resolution or higher hourly data from EUV. I looked into this correlation, which was changing, of course. In some cases, it's really difficult to see that. But the interesting thing was this delay. So the the lag of the ionosphere reacting on the 27-day solar cycle. So it changes through the year, goes from say about 15 hours or so to about 20 or more. Then at the end of the year, it goes down, then goes back again, goes down, and again, and so on. Well, I have it in the backup, but I don't want to show the figure. This was for 24 north, 42 north, but he looked into this also for the southern hemisphere and found that it was the same thing. So it's not a seasonal cycle, but a seasonal effect, but it seems to be more an effect of magnetospheric variability. So you see here also this annual variability of Kp, what he's shown here for comparison. And it goes down when the Kp is also this regular. And what we also were able to model this variability here. If we put in this magnetospheric variability together with the real solar flux, together with the real solar flux, and were able, and Rajesh and Eric, they were able to reproduce this variability here. So this is not a seasonal effect, which was wanted to show. Okay, this is the delay. In principle, this is to a certain degree the same than the figure before, but now for 30 degrees north to 70 degrees north, and taking the 3 years together. And there you also see that from the very relatively short delay to a longer delay through the year and then going back. And the next thing is, especially during, let's say, summer or so, that you have a seasonal, that you have a latitudinal distribution with shorter delay at high latitudes and a longer delay at low latitudes, which which one can see here. So this is from observations. This is from observations and GPS observations, and there were also, so in principle, let's say at 15 degrees east, you can see it here. This is the blue curve that shows a little bit, so what is shown here for 40 to 70 degree, 15 hours to longer, to a longer delay and a little bit back. This could also be modeled. So this is model results, which also show that at high latitudes, the delay is short, and at low latitudes, the delay is longer. The delay is longer. Yeah. So I still have two slides that to a little bit, let's say, not investigated. So it's not really finished. So I'm still going on, but there had been some hypothesis that this delay is also due, at least modified by transport. The usual thing is that you have ionization and you have recombination, for example, shown like here. So the electron density is somehow due to ionization and recombination that you get to O and N2. So this O over N2 is one parameter to investigate or to have a look into this ionization process or electron density process. And well, if you have this 27-day cycle, well, in principle, the density goes down, the temperature goes up. And if you look very carefully, you see that these cycles for O and for N2 is a little bit different. So here is the O over N2 shown here, and you see the gray line is this solar cycle, what was introduced in the model with the maximum here, and O over N2, so the electron density comes a little bit later. The three lines are for three different transport processes. It's just the diffusion coefficient that has been changed. And so one can see that if you increase diffusion, then transport is increased and you have a shorter delay. And for reduced diffusion, you have a slightly longer delay. This you can see here in another figure again. Here is the solar variability. What is shown here? Here is the TEC, global TEC. What you can see with the lag, and if you analyze the lag, you can see it here. It goes from 25 for weak diffusion to 20 hours for so for lower time scale for stronger diffusion. Okay, and the last thing is, I think I can really skip this one. I have another figure that shows that this delay is also height dependent. Of course, as it is recombination and ionization comes at different time scales, so this is particularly something for the F region and not so much for the lower ionosphere. So you see that the delay is longer in the F region, and in the lower region, in the lower ionosphere, it's shorter. So this is, you come to the 17 hours or so if you take everything together. And again, you see that this delay, this effect reduces if you have increased transport. Okay, so that's not conclusion, some summary or so. So that total electron lags, the EUV globally, but also on local scales. We have shown some global pictures and some local, more local results. This is about 15 hours at high latitudes, but more at low latitudes. And there is a seasonal cycle, but this is connected with geomagnetic activity and not so much with the season itself. This delay increases with solar activity, at least under idealized conditions. If the atmospheric influence is neglected, you can see it from the model. It's due to different response times, ionization and recombination, but it's modified by transport. And we can model it. We can model it, include the seasonal and the solar and this geomagnetic influences. And so have at least some idea on sort of for construction, for example, of empirical models. Okay, so that's all. Thank you for your attention.
Thank you, Christoph. We have just a few seconds for a question. I see one from Lindsay, Charlie Lindsay, isn't Earth rotation important?
The Earth rotation. Okay, not at least we didn't see it. So not sure what it means, whether some modulation of the Earth rotation that we didn't see, and we just for this analysis usually we took out some effect of diurnal cycle. I'm not sure whether this answers this question.
Okay. Lindsay adds, for example, the dark side of the Earth has to wait hours before it comes into exposure of a UV enhancement.
So yes, yes, of course. So of course you have a diurnal cycle, but so this was what we removed from the analysis, what we did, and so if we analyze this on, let's say, on a on some latitudinal cycle and go in with the sun, for example, and analyzing this at a fixed point, we got more or less the same results. So it didn't change the results, and so there was obviously not so much an influence on that.
That's interesting. I think we should move on. Thank you, Christoph.
Thank you again. Oh, very